Okay, so let's talk about this case study, and I have to move my laptop to whoever wants to talk. Just the recording will be a little bit better, and because we all have access to Moodle, so you see what else people have done, and my really quick skim through makes me believe that people are doing very similar things, I guess. But it would still be nice to have someone or some of you talk about the reasoning behind why you chose your modeling that way, and especially like talk about the results, because in the end you would like to determine whether the way that you're modeling it tells you something. So I posed the question saying that whether there are naturally two groups over there, like the first 5 are randomly guessing, while the second 10 of them are actually having better knowledge of the material, or maybe they have higher chance of guessing it correct, or whatever that is. So what do you think your modeling can help answer that question? Anyone? It's the last lecture. Yeah, I mean, if you, okay, so if I can bring up your write-up, and then if you want to use that too.
Yeah, it's like instead of doing the hierarchical, we did this latent clustering.
Okay, give me a second. Let me figure out how I can share. Give me a second, sorry. Yeah, you can just scroll through and then talk to the laptop.
Okay. Yeah, this is, we did a keep sampler where we have full conditionals, and it's like in homework 5 where X is the number of people who belong in one group and it's random, and the n-X number of people who belong in the other group. And instead of having priors of probability of answering correctly between the two groups, the probability of answering correctly, as we have here, is influenced by the number of people who are in the particular group in each iteration and the sum of their test scores. And ultimately, like after going through a terrible chain, which has the, I don't know how many liked values, but we burned in every 100 and it was much better in the end.
So the earlier was not.
Yeah, it's the result was a very firm confirmation of that 10 of them studied and 5 didn't. And the distribution of test scores was pretty much similar, except that here I didn't draw the actual data histogram.
Can we stay at the graphs over here? So
This
the left
one?
what is the left one is what? Is
the test score distribution of people who are in a group who didn't study.
Okay, and that's not the data that's generated.
That's the posterior, yeah.
The posterior of what?
Of the probability of answering correctly times test score. So.
Oh, okay. Okay.
Or maximum test score. So,
right. So it's 40.
Yeah.
Okay. And the middle one is the group that knows?
The group that knows, yeah.
Yeah. What about the last one?
The last one is number of people in group that knows. Yeah.
Oh, okay.
It's not showing particular people, but
it's showing the counts. Okay.
Yeah. Okay. So the downside here is that we're assuming that in each of the group of people who know and who don't, the probability of answering correctly is the same. Unlike what the hierarchical model would allow for them to pick a different probability of answering. But we're giving a distribution to the people in groups who know and who don't, instead of assuming that they are that way.
See. Yeah, can we go up to the front when you showed the model set up?
Yeah.
Yeah, because on this, I guess, yeah, so it looks like, my understanding is you get Y1 to be the one, like the first 5 people's total score, right?
Initially, yeah.
Yeah, initially. So how did you make it random later?
Here, drawing each X, and based on the X, which group each person belongs to, we sum their test score into Y1 or Y2 or Y2.
Okay.
And then those Y1 and Y2 influence the theta distributions.
Right, so that's in the Gibbs sampler.
Yeah.
Okay. So the PX over here, so that's the density. Like you're using a base rule over there. Is that right?
The
like
density for each Xi.
The probability of getting to the first group, I guess, and then 1 minus P X's. Okay. And the way that you're getting those is from E and then D by norm evaluated at the two distributions.
Yeah.
Okay, makes sense. So how did you set up your P to be 1/3 in the first place?
This was just a prior value. Not prior, but initial value for the chain.
For the chain, okay. But P is the probability of, because it's 5 and 10. So Okay. Makes sense. Nice. So this is a mixture model.
Yeah.
Okay. Understand. Any questions on this? Because I guess now, like reading it more carefully and based on explanation, I think this might be different from some other groups' way of doing it. So maybe we get another group of talking about what you have done. Because this one is mixture modeling that we let each person's assignment change every time. Okay? Yeah. All right. Let's keep in mind what we did over here. But what else? We have other people's stuff over here. Anybody did it in a similar way? Or not? Yeah, Tony, so let me bring yours.
We did it in a little bit of a different way. We assumed that there were two groups of people.
Do you mind if I bring this up and then this case study? Yep.
So we assumed there were two groups to start with, and so we split the groups into like the guessing group, which was the first 5 students, and then like the knowledgeable group, which was the second 10. And so we actually created 2 separate models for each of them. And we set a prior for the first group, like around 50% for answering any single question, because that was about what they got on the on the actual test. And we let the probability differ by each individual. And then for the second model, we set a uniform distribution from 0.5 to 1 for the probability that they got any question right. And since we cut it off on a lower bound of 0.5 because they all were answering about 30 out of 40. And so then we ran the model and we thinned and burned in to reduce the autocorrelation. And then we didn't put these in a graph form, but right here you kind of see this first output is their average proportion of their average correct rate in the Markov chain, and then the second column is the perceived average that we saw in the 40 question test. And so we see that for each individual, the chain pretty much mimics the truth, and then this second output is for the knowledgeable group. And so we pretty much just concluded that there are 2 groups, and one seems to be most some level of knowledge, which differs by individual.
Good. So this case, I guess it's mostly, the biggest difference between these two, first of all, is Nick's group, you let it to be random, which group each person belongs to, while Tony's group is you based on, say, if you look at exploratory data analysis, you see 2 big different groups based on their scores. So you might just let the first 5. So I think this is what they did over here. You let the first 5 to be the first group, and then the last 10 to be the second group, and you run 2 separate models, right? But I think the flexibility, so first of all, I think, they're good and bad to both. And the flexibility in this modeling in particular is once you break it into 2 separate groups, what you do with them, right? So here you have each person gonna have, so here's beta 10, 10. I guess that's the success probability, right? Guessing probability. And then each person will have an individualized success probability. So you can model from there, right? While the second one, so I guess because I was trying to give some hint over there in terms of how you can code it up in JAX. So this particular code that Tony did over here is you are doing a uniformly draw truncated between 0.5 to 1. Okay, so this again is an individualized probability that you think each person might just have a success probability uniformly distributed between 0.5 and 1. Okay, so that's what the code does. And then of course down here will be a random binomial draw of the success probability out of the 40 experiments or 40 questions that you do over here, right? Okay, all right. But of course, Nick's stuff earlier, allowing people coming from different groups across the chain will also, that specifically is a extra model that you assume that there are two components over here, and then one person, each person at each iteration based on like the probability evaluated, you might come from the first, you might come from the second. So I think, yeah, if somehow these two can be combined, I think that might be even better in a sense that you not only assume that people's assignment might change, right? But then at the same time, people's success probability individually has its own distribution. Okay, anything else? We got some other groups here. And have you done similar stuff or any other contribution or differences, major differences or major similarities that you have done? All right, if not, I can show you the way, it's not, I wouldn't say it's perfect, but I thought there's another way that we can combine. So the approach that I came up with is pretty much like combine both of the methods that we talked about. But I want to show you specifically the JAX code to do that, and what does it mean to have a model in that way. Okay, so okay, yeah, it's here. All right, so the way that I did it, if you look at the screen over here, so first of all, I assume that each person belongs to one of the two latent groups, okay? And the probability that I put over here, so you see so P is the number of persons in total, so it's 15 over here. And Z is a indicator vector, tells me which latent class the person goes to. So I use a D Bernoulli. And I use 0.5 over here, which is actually questionable, depends on what you want to do. Because earlier, I think Nick's choice was kind of 1/3, right? Because based on the data, you think, oh, it's 1/3 possibility of going to the guessing group, and 2/3 goes to the knowledgeable group, I guess. And then, so maybe you can put 1/3 here instead of 0.5. Okay, so that's something you can change. But overall, if you believe that each person belongs to one of the two latent groups, this is the way that you can set up the latent classes. And then what I did over here is I assumed the first group was just doing random guessing. So I put a probability. So this theta, I think other people's notation, okay, theta 1, theta 2. But here I was just using a different psi Greek letter notation over here. So I assume, I don't think this showed up, but okay. Yeah, and then let's see. Yeah, so I was assuming that the first group was just doing guessing, so I give 0.5%, 0.5 probability for that theta 1. And then the other one I was doing similarly to what Tony did. I had d beta 1, 1, which is uniform, and then truncated between 0.5 and 1. So I assume that the second group has some unknown but greater rate of success, okay? Right, but different from what Tony did, I didn't have an individualized probability over there, which will be a natural extension next. Yeah. And lastly over here, the way that I can determine, so I noticed, say like Nick, you guys wrote it out like in the loop to decide to check which group it belongs to. But if you do it in JAX, one useful code function to use is this equals, okay? So if you look at the theta, so theta is the success probability, okay? For theta I is the success probability for the ith person. So what I did is I'm checking if zi equals to 0. Okay, so this equals, and then zi, 0, it's going to be 1. If it is 0, it's going to be 0 if it is 1. Right, this is confusing, but it's pretty much helping me to check whether the the ith person belongs to the first group. Okay, if it belongs to the first group, I'm going to multiply with my psi, which is 0.5. Okay, if it's going to be from the second group, I'm going to multiply with phi, which is the greater unknown probability between 0.5 and 1. Okay, and then lastly, it's going to be a binomial draw, and n it's 40 because there are 40 questions over there. Okay, yeah, so this is, I mean, not perfect. I think one natural extension will be adding the individualized success probability over here, like what Tony did. And then, of course, you might want to change this 0.5 to, I don't know, 0.4, 0.3, and things might change as well. So I would say, I will post this in case in the future you ever want to do anything similar. But this, again, if you were to use this mixture modeling, what Nick did and his group was just using what we learned before and coded up the Gibbs sampler by yourself, right? But here is Jack's code, how you can do a mixture model. And the way to do it is, I would say, pretty straightforward. You tell R, like how you're gonna assign people based on which group they goes to. And then once they go into, you're gonna have different success probability because it's random, it's a guessing game. And then in the end, you're gonna do that. Yeah.
How did you do the data summary?
Right.
I tried to do the same thing with the latent variable, but like for each iteration, you don't have the same number of people in each group.
Good question. Yes.
So that's like really hard to get.
Right. Good question. Yeah. So I haven't done this in this write-up, but we can talk about what we can do. So Arin's question is, now if we do the mixture modeling, you have two groups, right? So how can we summarize things? So imagine now we have 15 people, right? And say if you have 10,000 iterations, so in each iteration, you're gonna have a vector of this z length of 15. And it's gonna be 0 and 1, right? So which is, I guess, Nick, your group probably didn't do it either, but it would be something interesting to check, is across the chain, you might be able to follow, say for one individual, for the entire chain, you have 10,000 iterations, right? So you might check, say, across the 10,000 iterations, looking at the Z1 to see for the first person, how many times the person was grouped in the first group and how many times it was grouped in the second group. Yeah, so that will be, I mean, actually so here it's simplified because we only have two groups, but sometimes if you want to do mixture modeling, you have multiple components, it's actually worth checking, like, say, whether most of the components are being occupied. Because sometimes you might want to shrink the number of components you have, or you want to expand the number of components you have. In this case, you only have two because, I mean, you can actually have more if you want, but based on the way that I set up the problem, I said, oh, maybe we can see two different groups. So we might think about two components, but in theory, you can expand that to even more. Yeah, so to summarize that will be something interesting to look at. And if you have more than two, like even larger, like 10, 20 different components, then it will be interesting to follow one person or some good selection of people to see how they're being assigned each time. And then in the end, when you're trying to, say, do summary of the results, if you have two groups over here, then for example here, it will be interesting to look at this side, the posterior draws of the psi, as well as the posterior draws of the phi, because that's at each iteration, it tells me what's the success probability for the two different groups that I'm doing. Yeah.
But the psi does not follow a distribution.
Oh yeah, sorry, yeah, so psi is fixed over here. Yeah, I should, right. So another thing I guess you can do is, if you're gonna do a uniform between 0 and 0.5, then you'll be able to like track that along the way, yeah. But overall, I think if you want to check if the model is not a bad fit, you should also try to do posterior predictive checks. And then to do posterior predictive checks over here is you're gonna generate new new experiments results, right? Like you can generate new people's scores and like generate 15 of them and to see if it's going to replicate what you have in the model, in the original data. Okay. All right. Yeah. So I'll post this online, and you might be able to expand this into even more advanced modeling techniques. And okay. So now let's maybe if we all know about case study 3, like from your old group, we can just keep it what we're doing right now. So you can talk to the other group, the non-group members about the case study 3. And then we're going to bring back as a whole class.